Hello, in today's video we are diving into how forces other than gravity do work in our work and combining this with our idea of the work-energy theorem. When forces other than gravity is acting on an object, we denote it as work, and then we're going to write other. I like to write just WO because writing other every single time takes a while. Like you can write WO. But how this combines to the idea is you have a total work. So our work energy theorem looks like this. You have your total work is equal to the change of kinetic energy. So you have the final minus the initial. So this total work right here is whatever work is affecting the object. So you write work, the other work that's other than gravity, is equal to, we can erase this. Well, obviously there's always going to be gravity unless you're in space. So you're going to write work other is plus the work of gravity, and then we write that equal to work total, and that's how we combine it to our work energy theorem. As shown, the equation of total work is the sum of the work done by gravity and the work done by this applied force over a distance. Now let's apply this work energy theorem with forces other than gravity, and in a case where it's affecting, let's say just a cube for example, we'll have a external force, like let's say somebody's pushing on this cube, and the ground's gonna be frictionless, just to make it simple. So you'd write, by figuring out how your equation's gonna be, obviously there's always gravity working on this object, so it's gonna be included. So work total is equal to final kinetic energy minus initial kinetic energy, and then we substitute the work done by, let's write our displacement, our work done by our work other, which is the force that this guy is applying. We'll just write an F here so we can know exactly what we're talking about. And then the work, so this came from work other. This work other can be friction, it can be a force someone's applying. It's pretty much just like a catch-all in our case here. And then we have the work of gravity, we'll write Wg is equal to K2. And normally when we sort up our formulas, we want the initials to be on the left side and the finals to be on the right side. So we break this into its components. So work done by force, it's just going to stay how it is right now. And then we'll break up the G, which is going to be initial for potential energy minus final initial energy is equal to the final kinetic energy minus the initial kinetic energy. Hold up, my cat's trying to get my mouse, my computer mouse. Makes it hard to push it around. And then we'll bring this up to here. So now this is going to be our final movements of our things here. So we're going to write K1 plus initial potential energy of gravity plus our other work. We'll just write an O now because we know what it is. And then we equals to the final kinetic energy plus the final potential energy from gravity. And then this equation tells us that the work done by all other forces than gravitational potential energy is it's the idea of this change of energy relates to the mechanical energy, as we're just summing up the whole thing is basically what mechanical energy mean, and that's how we're going to break into that idea. So we will donate this as, I think we use E means mechanical energy, and it's just equal to the sum of the potential energy from gravity plus the kinetic plus by the work done by others. And that's how we get this. This mechanical energy, as long as the forces are conservative, like potential, gravitational, kinetic energy, and then let's say, for example, spring tension, this kinetic energy will always be constant in our problems. The only case it will ever decrease is if you have friction from an object, which converts some of this mechanical energy into thermal energy, and that's a case where it's not, that doesn't hold true, where it's constant. So and I'll give you, you can kind of tell if the work utter is positive, this means that you're increasing this total kinetic energy, because this work utter eventually becomes either kinetic or potential. We're just writing it here to show all the forces. And if this is positive, it will be increasing the total mechanical energy, but if it's negative, it'll decrease it. We can also notice that the work utter from our previous page is, if we set this to 0, we get our previous work-energy theorem that we all know and love. So you just get K1, so you set this to 0, and then you get UG1 equals final kinetic energy plus our potential gravitational energy. This tells us that mechanical energy is constant as before, as long as these are conservative. And now we will go on to a problem to demonstrate these ideas we just talked about. So now imagine you have a 2 kilogram box. We'll draw our box here, and we're going to push it along in a horizontal distance. So we have this displacement right here, and then we're going to have our stick figure pushing this box again, which creates a force going in this direction, as long with this gravitational pull. You can see that this is going to be technically 0 since it's in the direction of displacement. That's why you don't include mg in our as the work utter, because basically the idea of work is equal to a force over displacement times the cosine of the angle between them. So you don't see this because normally when they're in the same direction, we know that the angle between them is 0, which is just 1, which just gives us force times displacement. But if it's 90, for example, for gravity, which is a 90 degrees angle toward displacement, this is actually no work. So we're not going to include that in our work utter. We apply this gravitational potential energy in our work-energy theorem, but if the change of y is 0, we know that's just 0. So now that we explain that, the mass of this box is going to equal 2 kilograms, and the distance equals 3 meters, and this force that he applies equals 10 newtons. So how much work is applied to this box is going to be a first question, and then our second is going to be what is the final speed. So what is V2? And a good way I like to solve this is to start by listing all my variables. So we know this box starts with a 0 velocity, as it starts from just sitting there statically, and we know that our change of y are both equal to 0. So we're going to equal, we know that's just going to be 0. So now let's find our work. So it's going to be 10 newtons times 3 meters, which is equal to 300 newtons. Pretty easy, right? Now we're going to go find what is the final speed of the box. So we'll write down our work-energy theorem with the other force and gravitational being applied. So we have the initial kinetic energy plus the potential energy plus the work of the other, which is going to be F, equals the final kinetic energy plus the initial potential energy. And you know that, let's change our colors here. This goes to 0, this equals 0, this equals 0, and we're just left of these two. And we know that because the kinetic energy equals 1/2 mass times velocity, and when this is 0, and potential energy equals mgh. So when this y change to coordinate is 0, this stays 0. So that's going to give us an equation of, we're going to say work utter equals 1/2 mass times final velocity. And now we'll just solve for final velocity, which equals, here it's going to be 2wf over mass. And now we'll solve for this using our calculator, so it's just going to be 300 in here over 3 meters. And this is going to give us velocity. Let's get our calculators out and solve for this right now. So it's going to give you 2 times 30 divided by 3, and that's like the square root of 20, which should give you, what's square root of 20, which gives you 4.5, we'll just round it up, 4.5 meters per second. And also, while you're looking at this, you can always check your units here. I just noticed that this is wrong right here. It's not 3 meters, it's 2 kilograms. Because to make sure you never make any mistakes, you should always look at units. So newtons is equal to kilograms over meters. This is times 2, and it then you have second squared over your kilograms. Kilograms are going to cross out. And then you also have your displacement, which I think is applied since work is equal force over a distance. So this one, this is not newtons, this is joules. As you can see, checking your units is always a good thing to do to make sure you don't make any silly mistakes. So 300 joules. Joules are equal to kilograms over meter squared over second squared. And yeah, and we'll get our final calculation here in a moment. So we're going to have 2 times, oh geez, it's going to be the square root of 300 since these two cross out. So that's going to give us 17 meters per second. Let's write that down. So V2 equals 17.3 meters per second. And I hope you enjoyed watching this video, and don't forget to like this video to motivate me to create more videos in the future.